Welcome. Thank you all for joining. My name is Don Andrus. I happen to be in Los Angeles, California, which has its own set of issues, right? We won't go into that. I graduated from Syracuse in 1968 in arts and sciences with emphasis in mathematics, went on to Purdue University, and actually had my master's in computer science in the dark ages from there. I've since worked for a little over 35 years for a company called TRW, which was bought by Northrop Grumman. And why is that important? Because TRW actually won the contract to build the telescope that we're going to be talking about today, the James Webb Space Telescope, in 2003. And almost a couple of decades later, it was launched on Christmas of last year. So I have great interest in this, as well as it's not only about space, but to see if my company really did do a good job here. I'll have to say I had nothing to do with it. So don't blame me. Let's see, before we begin, just a couple of housekeeping chores here. Make sure you keep your microphones muted, because the background noise really does interrupt what Professor Freeman is going to speak on. And I think that we are recording this just in case anybody needs to look at it later. And that'll be shared. Let's see, you can ask questions at any time. I always think it's probably best to let Professor Freeman get through his speech and then ask questions, but that's up to you. If you do have a question, either raise your hand in the Zoom function, which is, I think, at the bottom of your screen, hopefully. Or put a question in the chat. We'll be monitoring the chat between myself and a couple of the Syracuse folks. So without further ado, I'd like to introduce Professor Freeman, Walter. He's an associate teaching professor in the Department of Physics in the College of Arts and Sciences. He teaches astronomy, computational physics, engineering physics, and conducts research into computational methods for lattice quantum gravity. God knows I know very little about it. He's a native of Huntsville, Alabama, which is also known as Rocket City, where he grew up and listened to the NASA engineers test space shuttle engines across the town, and to the stories of the old rocket scientists living around. I happen to have overseen, as part of my career, a bunch of our folks that were in Huntsville, Alabama, and have been there on occasion many, many times. I did not run into Walter, of course. In his astronomy course, he focuses on bringing together the technical as well as the human to illuminate the value of science into our society. So with that, I am very excited and happy and pleased to have this opportunity to introduce Walter, and we'll turn it over to him for his presentation. Thank you. Walter?
Thank you. So please feel free to type anything in chat anytime. I have chat in front of me, and if we want to have this as a kind of a real-time presentation, then that works for me, right? Because I can see anything that you say in real time, and I can respond to it right away. All of us professors are kind of used to this, teaching Zoom school, so I am happy to talk in real time with you. This presentation is not just about the James Webb Space Telescope, although I'm going to show you all the pretty pictures at the end, right? This presentation is about how we got to the James Webb Space Telescope. And where I'd like to start, which way do I need to stand? Where I'd like to start is actually here. So this is the telescope in Holden Observatory in Syracuse. It was built in the 1870s, so it's a very, very old telescope. This is a picture I took with my cell phone camera today. And this presentation is really not just about this, but it's about this, and why we're not building telescopes like this anymore, and why we had to build this thing in order to find out the secrets of the universe. So this is a from here to there presentation, and I hope you'll find the journey to be as interesting as the destination. So what am I going to talk about? We're going to cover what a telescope is anyway, by using our telescope in the Holden Observatory as an example. We're going to look at why these things have to be so darn big, and why the engineering challenges in making them big are worth pursuing and how we do that. We're then going to look at some of the challenges that telescopes on Earth have faced. Why is the atmosphere annoying? And then the details of how we teach telescopes to see color, and why, I need to get out of the way of my words here. I didn't plan this too well. I'll come over here. Why teaching our telescopes to see color in ways that we cannot see with our eyes is so important for doing science. We'll talk about the first famous space telescope, the Hubble Space Telescope, and what it can do. Talk about the challenges that Hubble faces in answering some of the most interesting questions, and then look finally at why we needed to build the James Webb Telescope. So what is a telescope anyway? Well, first, it's really just a big eyeball. And I really hope you all will forgive me. I need to give myself a little bit more room to stand. So my slides are going to move a little bit further to one side. And now I have some more room to stand. Sorry about that. We've had tech problems all day. The telescope is just a really big eyeball, right? So in your eyeball, you have a lens out front that focuses light coming in from scenes around you. The lens focuses that light and projects an image here on your retina. So that's the physics of an eyeball. It's also the physics of a camera lens. So I have one right here. So this is an ordinary camera lens. I use it to go bird watching. So light comes in this end. It travels through the body of the lens and is focused somewhere back here. And well, we put a piece of film or a digital sensor right here, and we can capture the image focused by this lens. And the telescope in Holden Observatory is just a really, really big version of the lens I just held up. We can control the magnification of the lenses we create with our telescopes by changing their focal length, right? We can use either a more or less magnified image to zoom in or out on things. But ultimately, there's a limit to how much detail we can see, as you'll see later. Now, things are complicated a little bit if you want to look through a telescope with your eyeball, right? So if I am using an eyeball, right, the lens in my eye focuses light on my retina, and my brain knows what it is. If I'm using a camera lens like this, light comes in here, it gets focused over here, and then I have a piece of film here to detect whatever that light is. But then if I want to see it with my eyeball, life gets a little harder, right? And the analogy I like to use here is, I've clicked on the wrong thing and now I can't see Zoom chat. The analogy I'd like to use here is an eye doctor, right? It's very easy to see the image your own eyeball makes. But if you want to see the image in somebody else's eyeball, focused by somebody else's lens, then, well, when you go to the eye doctor uses a magnifying glass to see what's in your eyeball. And we have the same thing. So I actually have with me a box that has the original eyepieces in it for the Holden telescope. So they're little things that look like this. I'm going to hold it here so the face detection algorithm focuses correctly on it. So these are little magnifying lenses that you stick in the back of the Holden telescope to see the image that it makes. And this is only just so you can use your eye rather than, say, a piece of film with it. And here's a modern example. This is a loop that we might use to look at pieces of film or to very small objects. It's the same sort of machine. So we don't do this anymore because we don't look through telescopes with our eyes. We use film or digital sensors to collect the images. So we don't have to worry about that. So telescopes, they don't just let us see distant things, they let us see faint things. So this great horned owl here has very large eyeballs because it hunts at night. And the bigger the eyeball, the better you can see at night. So if you want to see very faint things in space, you need very big eyeballs. You need a very large telescope to gather as much light as you can to see a dim image. So I have a camera lens here. This is a wide angle lens that does some other things, but it has a kind of ridiculously wide aperture on the front, so you can take pictures of the dimmest objects in the night sky. I use this for night landscape photography. Those of you who remember your middle school geometry know that the area of something is proportional to pi r squared, right? So if you make the radius of a telescope, r, bigger by a factor of 10, you make the area, and thus the light it gathers, bigger by a factor of 100. So this is one of the reasons that telescope designers are always in pursuit of bigger telescopes, is to see faint things. But a surprise is that a bigger telescope actually lets you see more detail as well. It turns out that when you shoot light through a little hole, it spreads out. This is called diffraction. And the bigger the hole you make, the less diffraction you get. And here's kind of an example of this. These are images taken from an ordinary SLR camera, not by me. They were taken by Bob Atkins, who's an online photo blogger. And as we know, a telescope is just a very large camera lens. So what Mr. Atkins did was he successively reduced the size of the aperture in his lens. So this picture of tree bark has an aperture of 75 millimeters, and this one has an aperture of 9 millimeters. And you notice that it is very, very blurry. Why is it blurry? Well, smaller aperture means that the light spreads out. So if you want sharper detail, you also need to make a bigger telescope. So big helps you both with faint and with small. I need to stick my slides back to where they were. Yeah, so you can see the whole thing. Give me just 1 minute to click on something. We'll put the slides back here. There we go. So a little mathematics from physics. This is the only math in this talk, so don't worry, there's not a bunch of math coming. You can actually calculate the smallest detail that you can see with any given telescope. It turns out it depends on the wavelength of light, which we will talk about a lot more later. And I just did kind of for fun. We know how big one of Galileo's early telescopes was. It was 26 millimeters, or about 1 inch across. So if you stick this into the how small of detail can you see formula, you get that Galileo could see structures that were as small as 50,000 kilometers out at the orbit of Jupiter. Why is this important? Well, Galileo saw Io, Jupiter's closest moon, or closest large moon, with his telescope, and that's 500,000 kilometers from Jupiter. So it checks out that Galileo could see Io, Jupiter's closest large moon, with his primitive telescope that he developed. Well, so this is the Holden telescope then. It's just a giant camera lens, and people kept trying to make them bigger and bigger and bigger. Here is a telescope that has a 40-inch aperture at Yerkes Observatory. You might recognize, he's too small to see, but Einstein is in that picture. And this is just a gigantic instrument, and they got even bigger than this. But the limit is that lenses get big, they get expensive, and they get heavy as you make them bigger and bigger and bigger. And the pictures that they capture aren't perfect. They suffer from something called chromatic aberration, which is the idea that lenses don't bend all colors of light the same. And you wind up with pictures that look like this. So this top picture is sharp, is a good picture, but this bottom picture has red, green, and blue all focused in different places. And we don't want our telescopes to do that. You can sort of correct it at the cost of making your lens even bigger, right? So how do we overcome this challenge? Well, you use mirrors instead. You take the optical path that light would follow from a lens, and instead you bounce it back and forth between mirrors. So in this example, right, we have a telescope where light comes in the front, bounces off this mirror in the back, and then is focused at this little red X here, where we would put a piece of film or an image sensor or something like that. And this is the design that the James Webb Telescope has. Also, mirrors don't suffer from chromatic aberration because all colors bounce the same. And to kind of demonstrate how big of an impact this can have, so this is me with the Holden Observatory telescope. I took this picture this morning. So it's basically that big. And we've got an entire building devoted to that telescope, right? Over here, I'm looking at too many computers. Over here is the Holden telescope. It's like 4 times taller than me. But, and you'll have to indulge me as I go behind my camera, I have here in my office a telescope that's actually better than the Holden scope. It's bigger and it's more capable. And like, I've got it right here. It's on a tripod. It's sitting in my office in front of my chalkboard where I've been teaching students stuff. You can get one of these for a few $1,000s. This is what making telescopes out of mirrors rather than out of lenses has allowed us to do. We can now get big instruments without having to get such heavy ones, right? We can use really big mirrors. Just as a note for everyone, I have a piece of equipment that is battery powered that may die soon, and I'm going to switch to backup batteries. But if I do that, everything will be okay, and it'll take just 10 seconds for me to switch batteries. Another problem is that the stars twinkle. As the atmosphere passes overhead, the stars shimmer for the same reason that you see a hot stove shimmer. And this, maybe it's nice, we write songs about it, but it makes the astronomers grouchy because the stars aren't clear anymore. So instead, we now have our large telescopes with mirrors. We put them on top of mountains, typically in dry air, thin air, and very stable air. So to make the stars twinkle as little as possible. A very famous place for telescopes is Mauna Kea in Hawaii. This is at almost 14,000 feet elevation. And as you can see, there are tons and tons of telescopes that people have stuck up on top of the mountain. So now we've got big apertures. We've got, we don't need eyepieces anymore because we use film or digital sensors to collect our images. And now we know to build telescopes on mountains. What do we do next? And the answer is we've got to teach them to taste the rainbow. We have to get better at color than our eyeballs are alone. So even within the range of colors we can see, right, even within red to blue, our eyes are really, really limited. So this is a graph here of kind of the rainbow from blue to red. And these 3 peaks that you see are the sensitivities of the blue, of the green, and of the red cones in our eyeballs. And our eyes can't tell exactly where in the green or exactly where in the red something is. And if we get the sensation of orange, right, maybe we're seeing an intermediate wavelength here, like 575 nanometers, or maybe we're seeing, if we see orange, a mixture of red light and green light. And we have no way to tell with our retinas because we've only got 3 different chemicals in our eyes that see 3 different colors. So a solution, which we may be familiar with, is to use something like a prism, which you see here, this little glass triangle, to take in light, spread it out into all of the different colors of the rainbow, and then we can see which colors are present. So every major telescope in the world now has one of these attached to it. The other issue is even beyond the rainbow, there are more colors than we can see. So here's the range of visible light. We measure light's wavelength in nanometers. So the purplest, or wrong way. The reddest light is about 800 nanometers or 750 nanometers that we can see. And the purplest light is about 375 nanometers. But this is just a tiny, 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 tiny fraction of all of the wavelengths of light that are produced in nature by different things. So we see radio waves that have wavelengths of many meters, X-rays and gamma rays. Oh, I'm reversed. I'm looking at a backwards thing in my own display. Gamma rays, X-rays have wavelengths of tiny fractions of a nanometer. So the visible range is just this tiny little sliver here in the middle. And we're mostly going to be interested in this talk in visible light and the infrared that's longer wavelength than it. But just to demonstrate the value of being able to see all of these different ranges of wavelengths of light, here's a picture of the Milky Way, or many pictures of the Milky Way seen in different colors or different wavelength bands. So this one is the most familiar. This looks like a slice of the Milky Way that you see at night when you go out and look at it. And this is true color, right? The Milky Way really looks like this to our eyes. But all of these other wavelengths, these are things we can't see. So the only way we could show them to you, the only way NASA could show them to you, would be to map these colors onto the familiar red, green, and blue that our eyes can see. So people call this false color. There's nothing false about it. It's not a lie. It's simply taking the information we have about the light we receive in infrared or radio or microwave and mapping it onto red, green, and blue so we can look at it, right? So as you can see, there are vastly different structures visible in different wavelength bands in the Milky Way. We can learn different things from each one, but to really understand what's happening, we need all of them. We can also get a lot of information about individual stars from their spectra. So, but you see, all of them have little black lines in the same places. This is because they're made of the same chemical elements, and so is the sun. This is the sun spectrum magnified a bunch. Obviously, we have lots of light from the sun. We know it very well. It's close, it's bright. And every one of these little dark lines comes from a particular chemical in the sun. So my teaser, my recruitment pitch to my students to take my class is I say, there are holes in the rainbow, and they tell us that we are made of stardust. Because I can look at these two and say these lines come from sodium. There is sodium in the sun's atmosphere, just like the sodium that was on the potato chips that I ate for lunch. And all of the rest, we know what chemicals they came from. So the problem is that only a limited range of wavelengths comes through the atmosphere. So this is a doodle from NASA, a cartoon. So up at the top, they have graphed different wavelengths from gamma ray here, visible light, that's the one with the rainbow, through the infrared and through radio. And the higher the graph, the more the atmosphere blocks that kind of light. So the atmosphere blocks gamma rays, it blocks X-rays, it sort of blocks ultraviolet, that's the ozone layer. Visible light gets through, and a good thing, so we can see by it. It selectively blocks infrared, but this range of infrared it really strongly blocks, and then radio waves get through. So the only things that get through our atmosphere really well are visible light and radio waves. And this is a problem, because if you want to do astronomy, say here or here in these ranges of wavelengths, the atmosphere eats them all. Whoops, we can't do infrared astronomy from Earth. And the problem is we'd really, really like to, because the same chemicals in our atmosphere that absorb infrared light may also be in other planets' atmospheres, and we'd like to study them. We have a graph here of these, the gray bands are where the atmosphere absorbs, and they line up, right, with what's absorbed by water vapor. And if we want to know if water vapor is somewhere in space, we've got to be able to see infrared light of that color. Now, I need to tell you one more piece of physics, which is another reason why infrared astronomy is really important. This is called the redshift, or the Doppler shift. You probably know that if a train is moving away from you, its whistle sounds at a higher pitch. This works for light as well. So light from a star moving away from us is shifted to longer wavelengths. So here's a cartoon of how this works, right? So here is the original spectrum of a star, but if it's moving away from us, all of the features in its spectrum get shifted a little bit toward the red. So this line that was yellow is now orange. Everything shifted by just a little bit to the red. And when we study this, here's the problem. Everything we look at is moving away from us because the universe is expanding. The more distant things are moving away from us faster, and the oldest things in the universe are moving away from us super, super fast. I'm switching batteries. I will be right back. So we would like to study the oldest stars in the universe, but their wavelengths are stretched out by 15, 20, even 30-fold. And you guessed it, instead of producing the light that they normally produce in the visible spectrum, right? So here's the visible spectrum. Instead of producing this light, it shifted over here in the infrared where it's blocked by our atmosphere. All right, the solution seems obvious now. We just put a telescope in space. Stick a telescope in space. Now you can see into the infrared because you don't have the pesky atmosphere absorbing the light you want to see. So this is the famous Hubble Space Telescope. It's very small. I can hold it right here in my hand. Yes, the green screen never gets old. So what does Hubble do? So it is a telescope that can see visible and near infrared light put in low Earth orbit. I've given a wavelength range here from 90 to 2400 nanometers that Hubble can see. And here is a graph. We'll actually see this graph several times, but what does it mean? This white piece here is what Hubble can see, the wavelength range that Hubble can see. And this red blob that you see, that red curve, is the wavelength range that the sun and stars like it produce. So Hubble can see the ultraviolet light, the visible light, and a little bit into the infrared of light produced by stars. Great, we have a machine that will let us see stars. It will let us see near infrared, like these absorption peaks from water. So Hubble can tell us, for instance, where water is in space. You can't do this very well from the ground again, because, well, these absorption peaks where water is being absorbed, we've got water in our own atmosphere. Our own atmosphere screws up our ability to see this. But Hubble cannot see even longer wavelengths. And there's a lot of interesting stuff in those even longer wavelengths that we would like to see. Hubble, for a long time when I was a child, Hubble was the hot new thing. So this is the famous Hubble Deep Field image. It's a super detailed picture of some of the most distant galaxies known. You can even see, so you may see like little curves here, right? This is like a little arc. There's another one here. I'm trying to use my green screen. This is where the gravity of a star in the foreground, maybe this, or a galaxy in the foreground, where the gravity of a foreground object has actually bent the light from these galaxies in the back. So they look twisted because their light has been bent as it passes by things in space. So Hubble was the hot new thing when I was young. But there's a problem with the hot new thing. And that problem is that everything with the temperature produces light. I'm going to keep talking, but I'm going to step away for just one moment to make sure I don't have another tech problem. Everything with a temperature produces light. Things like stars are very hot. The sun is thousands of Kelvin. So Kelvin is a temperature scale, much like Celsius. The sun is thousands of Kelvin. It produces visible light. So that's why this side of my face is brighter than that side of my face. I'm standing by a window and sunlight comes in, right? The sun shines because it's hot. The hottest stars are tens of times brighter than the sun. Instead of producing mostly visible light, they produce mostly ultraviolet light. So stars produce visible light, who have a wavelength of hundreds of nanometers. But cooler things, like you and I, room temperature objects, Earth temperature objects produce infrared light. So I'm going to step in front of the words and point at my graph a bit. So this red curve here, right, this is sunlight modified by what the atmosphere blocks. But over here, you'll see 3 more curves. These are the thermal radiation curves coming from objects like the Earth. The Earth emits light too. You emit light, I emit light. My computer emits light a little bit more because it's warming up, but Earth emits light as well. And so do our telescopes, right? They have a temperature. And the problem is that Hubble, if Hubble is trying to see these very long wavelengths of infrared light, it is blinded by its own thermal radiation. The problem with Hubble is it's too hot. It emits infrared light itself. And then if you're trying to study the same wavelengths of infrared light, you're out of luck. You're blinded by your own radiation. And this is a problem because remember when I said that the sun emits these wavelengths that are visible sunlight that we can see? But the oldest stars in the universe may have this wavelength, may have this their light stretched out by a factor of 10, 20, or 30. So where this light is about half a nanometer, all of a sudden to see the very earliest stars, their light is stretched out to be, excuse me, not half a nanometer, half a micrometer, so 500 nanometers. So 500 nanometer sunlight is stretched out to 10,000 nanometer infrared light. I see your question, William, just one second. So the very, very oldest stars are moving away from us so fast that their light is redshifted into the same range as light coming from objects that's our temperature. William asks a super penetrating question in chat. They've said, do we ever see any spectra on Earth that get redshifted into the radio range so they can come through the atmosphere? That is an amazing question. Yes, we do. So stars, the oldest stars are redshifted by a factor of 20 or 30, but radio is all the way over here. We would need something redshifted way more than the oldest stars in order to be in the radio, even older than the oldest stars. But it turns out that the light from the oldest atoms, from the era when atoms were first starting to form, has been redshifted into the microwave, which comes through our atmosphere. So when astronomers and engineers and everyone pointed microwave receivers at space, they saw just a background of microwaves coming from everywhere. They didn't know what was going on, right? I mean, one proposal was even that it was bird poop on the radio dishes. But then someone said, you know, maybe there's a reason for this. Maybe there's a reason that space is full of microwaves. And it turns out those microwaves are echoes from the formation of the very earliest atoms, but redshifted by some unimaginable amount. I had to calculate it when I was in school, but I forget what the number is, but it's redshifted by many thousands of times so that it's in the radio instead of in the, I think it's ultraviolet X-ray, probably X-ray when it was produced. So yeah, this does happen. Redshifts all the way from X-ray to radio waves. And this goes back to the very earliest atoms in the universe. And that's an entirely different field of astronomy. The Webb telescope doesn't see radio, but people are very interested in studying that. And it's an active area of research to try to figure out what secrets are lurking in the microwave background. Great question. So our problem with Hubble is that it's too warm. It's blinded by its own thermal radiation. Well, the obvious solution is to make something that's cooler, and that's the Webb telescope. Webb is Hubble, but cooler and bigger. That's the one sentence pitch. So the point of the Webb telescope is to make highly detailed, blame whatever person wrote these slides, that's me, um, from the visible all the way down deep into the infrared. So how is Hubble better than, or how is Webb better than the other telescopes we've studied? You got to stick it in space, so there's no air. You got to make it big. Well, we've learned for a long, in the last, I don't know, couple of decades, that the way to make the biggest mirrors for Earth telescopes is to use a honeycomb pattern, so you can make little segments of the mirror and then put them together later. Well, to put this in space, we had to make one that we could unfold. So we had to do origami with hexagons, but NASA figured that out. But the really big thing is they keep it in the shade, so it's cool. The Webb telescope comes with a sunshade. It's 5 layers of fancy material that block sunlight from warming up the scientific instruments here, so they're not blinded by their own infrared radiation. Even worse, one sec, Henry, I see your question. Even worse, the Earth and the Moon, we produce infrared light. So you've also got to keep this in the shade of the Earth and the Moon. So Earth, Moon, and Sun all need to be down here. And the Webb telescope's been put in a fancy orbit, so all of the stuff near us that produces light, Earth, Moon, and Sun, is down this way to keep the telescope cool. Henry asks, do we know why the redshift exists? We do, in a sense. I don't have a good picture here to show you of this. I cut it for the interests of time. But the short version is, if you imagine something traveling away from you, suppose someone, here's a good example. Suppose someone is rolling a bowling ball every second. So they roll a bowling ball forward every second, and they roll those bowling balls at 1 meter per second. So there's a line of bowling balls behind them, all traveling however fast they're traveling, 1 meter per second, that are 1 meter apart. But then imagine that that person is walking away from you while they roll their bowling balls backwards, right? So they're walking away from you, throwing bowling balls backwards. They'll be separated by more distance, right? Because they roll one bowling ball, then they walk a little bit away from you and they roll another bowling ball. Well, now the distance between them is 1 meter that the bowling balls rolled, plus a little bit that they walked away from you. So that's an example with using bowling balls as a metaphor for light, but it works the same way for light. It works the same way for sound as well. So if you imagine a tuning fork that's vibrating and moving away from you, right? Its vibrations get stretched out as it travels away from you. This is much easier to demonstrate with a video or a picture, and I don't have one in my slides, I'm sorry. But that's a metaphor you can think about. So here is, let's look at, so here's the Webb telescope, here's why we built it, here's the technical achievements that it has. Oh, great question, Elizabeth. So Elizabeth has been reading up on Lagrange points and orbits. Does the telescope's orbit at the second Lagrange point account for the placement of the Earth, the Moon, and the Sun, or is there some other reason why it's at the second Lagrange point? So I didn't prepare a slide on Lagrange points. Again, it's a technical thing that I cut, but Lagrange points are essentially stable places in the orbit near the Earth and Moon and Sun. And so if you just put the telescope in some kind of orbit around Earth, it wouldn't stay put. We'd say, okay, well, we want the Earth and the Sun on the same side. Well, as it orbits the Earth, then it winds up between the Earth and the Sun, and that's no good. So Lagrange points are simply places where you can put something near the Earth so that its orientation with respect to the Earth doesn't change. So the Earth, the telescope, and the Sun all orbit together. And the L2 Lagrange point, which was what Elizabeth is mentioning, is simply the Lagrange point that's away from the Sun compared to the Earth. And it's about 1 million miles away, I believe, which is bigger than the orbit of the Moon. So this is how we get the Earth, the Moon, and the Sun all on the same side. We put the telescope at this magic place where it will stay put relative to the Earth if it is orbiting both the Earth and the sun together. So yeah, that's why we stuck it out there. It's just where we could put it, where it would stay put, where we could drop it somewhere and it wouldn't orbit the Earth like the moon. That's a good question. So here is the famous Hubble deep field picture I showed you earlier. This is a magnified bit of the middle, and you can see the gravitationally lensed galaxies here. But here is the picture from the James Webb Telescope of the same thing. And so you see the picture from the Webb Telescope is much sharper and has more detail. That's because its mirror is just plain bigger. Here are some other pictures. So this is another deep field image from the Webb Telescope. But here I've showed you two different wavelength bands. On the left, you see near infrared. So this is more like what Hubble sees. This is close to visible light. But over here, you have, this is dominated by these deep red distant galaxies. They're shown in red, but really they're far infrared. So remember, it's the really, really, really distant things that get redshifted deep into the infrared. Well, now they're really bright, right? These very distant galaxies show up super clearly in this long wavelength infrared image that the Webb telescope can capture because it is so cold. Remember, it being cold is the reason for the sunshade and the complicated engineering and putting it out at the L2 Lagrange point. It's so we can put it in the shade and keep it cool. But this isn't the first time anybody's thought of trying to do a cold telescope. We made something called the Spitzer telescope, which is also out at the L2 Lagrange point. But instead of using a sunshade, it's cooled with liquid helium. It's more limited, a lot more limited in its capacity. This is the previous best image we could get in the infrared. And here's a picture that Webb casually took in the same wavelength range. So much sharper, and that's because the Webb telescope is bigger. Size matters when you're doing astronomy. Here is probably the most famous of the early Webb science images. This is the cosmic cliffs image. This is from the Carina Nebula. And this is unique because stars are forming here. So a nebula is this dense cloud of dust and gas. And many of these stars that appear here are brand new. They've just started nuclear fusion. And there is, of course, way more information in this image than we can see with our eyes, right? Because we've got red, green, and blue cones, but the telescope can see far more detail in the spectrum of the infrared light that it captures. And astronomers can learn about the chemicals that are here, right? Because remember, if you look at spectra very, very carefully, you learn the chemical composition of the thing you are pointed at, right? By looking at the spectral lines. This next thing I think is even cooler. So this is not a picture from Webb, but one of the biggest question, right? The question everybody wants to know in astronomy is there life outside the solar system or outside Earth? Is there life anywhere else? And we know that, well, water absorbs certain wavelength bands, and all life on Earth requires water. So we'd like to know if there's water in space somewhere. And if you get above Earth's atmosphere, you can see the spectroscopic signature of water. So here's the trick. You wait for a planet to pass in front of a star. So this is Venus, actually, in our own solar system. And when Venus passes in front of the sun, it blocks a tiny little bit of the light. But its atmosphere blocks a little more. And you can see what's in the atmosphere. In this case, you can see what's in the atmosphere of Venus by looking at how the spectrum of the sun changes. Well, this is our solar system, but Webb can do it in other solar systems. So this is data from a NASA slide. I'm forgetting which star this is, but there's a star that has a very large giant planet, a gas giant like Jupiter, near it, and they have seen that the star gets a little bit darker when the planet passes in front of it. Well, that makes sense. But there's a little bit of extra absorption here, 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 and over there, and that's exactly where water absorbs. Hey presto, this star not only has a big planet orbiting it, but that planet has water vapor in its atmosphere. All of this from infrared spectroscopy. I want to show one more picture. This is just, I never get tired of our own solar system, right? We talk about all these fantastic things and supernovas, black holes, all of the exotica, the early universe, but I think there's so much yet to explore in our own solar system. And this is a picture of Jupiter that's kind of unique. We haven't really seen this before. And the really fancy thing is Jupiter has an aurora, like the aurora polaris, the northern lights. The north and south poles of Jupiter have an aurora, which is just amazing to me. I'll leave you here. I want to leave a lot of time for questions if you all have them. But I want to leave you with one more picture. This is a picture of someone doing cryogenic tests on the Webb mirrors to make sure that they work at low temperature, because of course they're going to be very cold. And this is done in Huntsville, Alabama, in my hometown at the Marshall Space Flight Center. So the people who were testing the space shuttle engines when I was a kid and rattling the windows, now at the same NASA place, they are working on the Webb telescope mirrors, and you can kind of get a sense of its scale from these people standing in front of it. So this has been a very whirlwind tour through not just one telescope, but the progression of telescopes from the one that we have in front of us in Holden Observatory, the one that, my students are actually over there right now. So from this thing built in the late 1800s to our new fancy, very cold infrared telescope in space that we hope will tell us things about the very oldest stars in the universe. So does anybody have any questions?
Yes, let's open it to questions. If you do, either use the raise your hand function or put a question into the chat. While we're doing that, by the way, obviously Huntsville is not as noisy as it used to be with telescopes versus rocket engines, right?
Yeah. Yeah.
That's a good thing, I guess. Let's see, there's my understanding is that the mirrors are actually plated or gold coated. And what's the reason for that? Do you know, by chance?
Why are they plated with gold? I'm not sure of all of the chemistry, but I believe the people making coatings need to make something that is a combination of durable, malleable, right? Gold you can beat into very fine gold foil, so you can make a precise surface with it, and also that reflects a wide range of wavelengths. Remember, this mirror is getting used for everything from visible light to deep into the infrared. So you need a mirror that will reflect all of those kinds of light well. And that challenge of making things reflect is actually super hard for people doing X-ray astronomy. And they have to think very hard about how to make mirrors that play nicely with their X-rays. Nice. Albert Linnell in chat says, what occurred that released what became the microwave background radiation? Wonderful question. So there's a concept in science of thermal equilibrium, the notion that two things have the same properties of temperature. And in the early universe, we didn't have neutral atoms, right? We had protons and electrons that were separate. So this was a plasma. The universe was made of electrically charged things. And light can't go through electrically charged things because light is itself an electrical phenomenon. So the thermal radiation that was flying everywhere was the same temperature as the universe. And as the universe expanded and cooled, eventually it got cool enough for protons and electrons to find each other, to stick together and make neutral hydrogen atoms. And it is at that point that the universe became transparent, that light could pass through the universe, essentially. And the light that could pass through the universe at that time, in the moment when background light and matter no longer bounced off each other all the time, the light and the matter could kind of go their separate ways, and they didn't have to be the same temperature anymore. So now all of this light is just left over. It's passing through the matter that's now electrically neutral, but that's what it became, the microwave background. So it's the thermal radiation from the very, very, very early time in the universe when matter first became neutral. And I still remember in my undergraduate education, like learning about this and learning about just how magical it was that you could study the properties of this thing and trace its progression from ultraviolet all the way to microwave where it is now.
There's a couple other questions.
Yep. William Anselm says, what's the exposure time of the Webb telescope versus the Hubble telescope to capture a scientifically valid image? Well, it depends on what you're trying to take a picture of, right? If I'm taking a picture of things in bright sunlight with my lens that I held up here, I might use an exposure time of 1,000th of a second. But if I'm taking a picture of something at night, I might need 10 seconds. So it really depends on how bright the thing is. But I think the question to ask is, how much less time does the Webb telescope need? And in this case, it's just because its mirror is bigger. So the Webb telescope, I don't know the number off the top of my head, but I would probably guess the surface area of its mirror is like 10 to 20 times bigger. So it would need 10 to 20 times less time to capture the same amount of light from the same object. And whether that is, scientific validity, of course, is, have you gathered enough light to answer the question that you would like to answer? Carol says, are stars living? That's poetic. So I told the story of the early solar system to my class one year, and a student who may be the smallest student I've ever taught, a very tiny, brilliant student from central China, comes up to me and she says, we often learn that the sun is our mother. But if the sun and the earth formed from the same nebula, from the same exploded star, then that star that long ago exploded is our mother, and the sun is really our sister. And then she wrote a brilliant short story about this that kind of made me cry as her final project. She graduated, I think, in 2019, and I don't know, I've kind of lost track of her now, but Jinying, where if you're here as one of our alumni, thank you for that story. Brad asks, how do we know when we've learned all we can from a particular telescope? I don't think we ever will. Can we still learn things from the old telescope over in Holden Observatory? Absolutely. Can we use it to do stuff? Absolutely. And it's not a question of when will we have learned all that we could learn, because there's always more to learn. But telescopes are often decommissioned when the cost of keeping them in operation is larger than the benefits that we would get. And if we took that money, that time, that human time, and we instead invested it in doing something else, we would have greater benefit. So I don't think we're ever going to learn all that we can learn from Hubble or from the Webb telescope or from the Keck telescope or any of the great telescopes of history, right? You could still dig them out and do lots of things. And in fact, I showed you the small telescope that I have just off camera here, right? This one. Citizen astronomers are using telescopes like that all the time. And they contribute in very real ways to the progress of cutting edge astronomy, simply because there are so many citizen scientists looking in so many different directions with so many telescopes. So an instrument doesn't have to be the best in the world or the best out of this world to contribute to science.
By the way, I just noticed a little thing on the web here. It says that the polished area of the Webb telescope is actually 6 times larger than the Hubble and measures approximately 283 square feet, which seems amazing to me.
Yeah. It's
Huge.
six times bigger. So I said 10 to 20, I was too high. So yeah, it's 6 times bigger. But yeah, that's what matters for seeing dim things is usually just how big is it.
Right.
We've got some other great questions. Elizabeth says, what do I think the next advance in telescopes will be? And do we need a technological revolution to achieve it, or do we just need to go build it? So that's a great question. There are many kinds of advances taking place in parallel. Many of you may have seen the famous glowing donut that is the Event Horizon Telescope picture of the black hole. So this is an advance in radio telescopes, an advance in something called synthetic aperture imaging, which you can read about. This involved basically electrical engineering wizardry. We could just keep up this business of making ever larger telescopes to see ever dimmer things. There's also, so at Syracuse University, we have built or contributed to building an entirely new kind of telescope that can see gravitational waves, which are not light at all, right? So I think there are lots and lots of these advances happening in parallel. I think the next big advances in astronomy are not going to come from advances in instrumentation, although those definitely help. The gravity wave people, like, that's an exception. They have a lot of room to improve on the LIGO detector, and they're working on that right now, right? But really, I think we've just launched this new instrument. I think astronomy is headed for a time when what's needed is people to make sense of all of the data. And making sense of all of the data is going to require very bright people, very dedicated people, a lot of diverse people with different backgrounds. Again, the advance in the Event Horizon Telescope, that really came from computer imaging and electrical engineering rather than telescope design. They're going to come in those things rather than some new instrument. I think, but never count out the ability of humans to prove me wrong by coming up with some very clever new thing. What are other, okay, so let me grab a couple of other people's questions. I'm going to kind of go in order. Do Webb and Hubble complement one another? Yes, they do a little bit, because Hubble can see visible light and ultraviolet light, where Webb is a dedicated infrared telescope. So Hubble can still see shorter wavelengths than Webb can. And we can't see ultraviolet light from Earth very well. So Hubble, is telescopes in space generally, but Hubble in particular are unique in that regard. Albert asks a really penetrating question. Are there ways to coordinate the data from space telescopes spread far apart? So when you say coordinate, there is a very particular kind of coordination that lets you essentially take multiple telescopes and combine their information to give you an effective aperture, right? We've talked so much about how aperture matters. We've talked about how making this big counts, right? You can get an effective aperture that's the distance between the telescopes you've tied together. It's almost like making a network of telescopes. The Very Large Array in Mexico does that. The problem is that that can only be done for longer wavelengths, like radio waves. Radio waves and microwaves, yes. Visible light and infrared light, so far, no. But you could put a whole bunch of radio telescopes in space and network them together to do even better than the Event Horizon Telescope. And in fact, in Carl Sagan's absolutely wonderful book, Contact, which proposes, aliens come to Earth and a scientist talks to them, is kind of the one-sentence story. It's an amazing book and you should go read it. But the radio astronomer who talks to the aliens, she winds up proposing a set of networked radio telescopes in space to investigate what is going on. So yes, this is absolutely a thing we can do. Chuck asks, is Hubble still working? Absolutely. It is still up there. We are still talking to it. We can still take pictures with it. It still does the same things that it always did. Actually, it does better things. You might remember that Hubble, initially they made the mirror the wrong shape. So we had to go up there and put glasses on Hubble for it to see better. Robert asks, what are the risks to the Webb telescope of micrometeoroid strikes? I don't know the entire kind of like the whole risk analysis. I do know one happened. So there was a micrometeoroid strike that did hit one of these honeycomb panels here and knocked it, either bent it or knocked it a bit out of place. And they did have to jiggle one of these back into place to compensate for the fact that it had been hit by a micrometeoroid. A strike from something large would definitely damage the telescope. We simply just hope that doesn't happen. There's stuff in space, but space is mostly empty, but there's always the risk. That's a really good question.
Let's see, it is a little bit after 5, and the SU folks told me I need to really keep this on track and on time, or the bell will ring for the next class, I guess. But I do want to thank you very much, Walter, Professor Freeman. Very interesting conversation, fantastic. You obviously have a lot of in-depth knowledge that is truly tremendous and a real asset to the university.
Well, thank you.
I'm very happy that we've all had this chance to hear from you. I'd also like to thank the rather extensive audience that we had. I think this is one of the best attended Alumni Academy events. I think I was watching off and on. I think we had over 70 attendees participate. So this is really good. Syracuse will be hosting more of these events, and they'll be, posted through the website and the emails, etc. And I hope that you all find these beneficial to you, and I hope that you participate in some others. So with that, I'd like to thank you very much. I'd like to again thank Walter. I learned a lot of things. As I said, I had virtually nothing to do with the James Webb Space Telescope nor space in general. I was mostly a ground guy. But thank you again. Thank you all for joining us. I hope you have a very happy holiday season coming up, and everybody be healthy and safe. Thank you.